So welcome back, everyone. So the topic of today's lecture will be stacks. So what we've been discussing so far is some of the theory and examples of analytic rings. And what's going to come next is how to use these to build geometric objects. The analytic stacks. And we already saw some a little bit of a clue of what kind of some of the kind of phenomena we want to include in this world of analytic stacks, and the discussion that Peter gave last time of the Tate curve over this gaseous base ring. But to motivate, so I don't think today I'm going to give the precise definition of what we're going to mean by analytic stack, but I do want to motivate. I do want to motivate it beforehand by talking about something in the world of pure algebraic geometry. So classical algebraic geometry. So what's the paradigm here? The paradigm here is, say you have maybe commutative rings. And you want to think of these as describing some sort of basic geometric objects, which are called affine schemes. So that's R goes to spec R. And that's kind of, those two categories are equivalent or anti-equivalent. The maps go in the other way. And then you want to use these to, so then you want to glue these together somehow. Or you want to allow yourself to glue these affine schemes together somehow to make more general geometric objects. So that's kind of the paradigm in algebraic geometry. And in this gluing, there are kind of two aspects. So the first one is, well, what kind of gluings are allowed? And the second one is, well, one version is how to identify different gluings, the results of. Or more generally, what are the maps? Or what is the category between the kind of formal gluings of affine schemes? So for example, so there's the classic P1, of course, can be thought of as taking A1, some plus version of A1 and some minus version of A1, and gluing them along a common GM via inversion. But of course, you want this object to have symmetries like PGL2, which don't respect this decomposition. So there has to be some kind of, there needs to be something said about what are the maps between different gluings. And it's actually, well, it's better to think of two first. So another way of looking at it is that you should specify an ambient category. which should contain the category of affine schemes which is kind of commutative rings op, and then single out another full subcategory kind of this, given by specifying certain allowable gluings of affine schemes in the larger category. And then that's kind of one way of describing a class of geometric objects in algebraic geometry. So, okay. So the completely, so the classical approach to schemes you take the ambient category to be, well, locally ringed spaces. So commutative ring gives such a guy, spec R, and then a scheme is a locally ringed space, locally isomorphic to some spec R, right? Or in other words, the allowable gluings between affine opens are just gluings along open subsets in terms of viewing spec R as a locally ringed space. But there's a more modern approach, which says actually we should we shouldn't try to be particularly clever about choosing an ambient category. I mean, we don't have to somehow think of the concept of a locally ringed space. We can just formally build an ambient category based on this category of commutative rings, and then just work there. So we want to build a category where you're allowed to do, say, arbitrary gluings of affine schemes, i.e. opposite to commutative rings. And the category where you can do that kind of thing is called the category of presheaves. So the category of presheaves on affine schemes is the universal category in which you can glue. Or more formally speaking, it's the colimit preserving, it's a category with all colimits with a functor from AF, and giving a colimit preserving functor out of this is the same as giving an usual functor from AF to that category. There's a set theoretic technicality here, so caution set theory. I'll discuss that a little more later. So this is not a small category, so you have to be careful taking functor categories out of it and so on, but okay. So that's you've formally allowed yourselves to glue, but you haven't explained how you should identify the results of two different gluings. But that's, so if you pass to sheaves, for some Grothendieck topology, that explains or how to identify gluings, or more generally how to map between two of these formal gluings. And the more covers you put in your Grothendieck topology, the more maps you're going to be making that might not be so evident from the perspective of the cover, like these automorphisms PGL2 of P1. But you don't want to add too many elements to your cover, or else you might destroy information. You might be identifying too many things. You might destroy some information. So there's kind of a delicate choice in the Grothendieck topology. And then, so for example, so you could take so you could take Zariski topology, and then schemes is a full subcategory of Zariski sheaves on affines, such that locally representable, locally in the sense of open covers. where you can define the notion of an open inclusion in this category just by reduction to the case of this, so by pullback, basically, reducing to the case of that. So yeah. So that's kind of the perspective we're going to take on defining analytic stacks from analytic rings. But we don't really want to take schemes as a model, because more general geometric objects come up and actually are relevant, and that's these stacks that I want to discuss now. So, well, please, of course, there's lots of people who who know all of this stuff that this is, you know, I apologize if the material I'm discussing is really familiar to you and you're getting bored sitting and listening. But I think it's good to give some motivation, start from common ground.
For this advanced scheme, do you fix a base field or a base ring?
So at the level of this discussion, let's say the base is Z, right? I mean, at some point, I mean, for some of my examples, I might have a base field, you know, just, let's keep it loose, okay? This is just motivation, yeah. So, yeah, why stacks? So, well, so often moduli spaces in algebraic geometry have the form, let's say X mod G, where X is a variety and G is a group variety, say, or scheme acting on X. So there's some quotient of some variety by some group of automorphisms. So for example, you can look at the moduli of elliptic curves, and let's say for simplicity that we invert 6, makes the discussion easier. Then this is X mod G, where X is spec, let's say, Z1 over 6, and then you give two scalars A and B, but they have to be such that the discriminant should be a unit, so you invert the discriminant, and then there's just a action by units, giving the changes of coordinates. So this parameterizes the elliptic curve with affine equation in this familiar Weierstrass form. And then it turns out the only isomorphisms between two elliptic curves given by that equation are given by some scalar multiplication with certain weights on the x and y variables, and that's this GM action here. Yeah, there's also many other ways of presenting the same stack. So for example, you can add level structure and then mod out by a finite group. So if n is sufficiently large, this will be represented by a variety, and then you quotient out by some finite group. And again, whatever the gluing that we choose should be such that, I mean, the Grothendieck topology that we choose should be such that the two things are actually identified in our category. So we should at least allow a tall covers into the story for this, and that is indeed the classic choice. So pass to a tall topology. And well, these quotients, for example, so these quotients exist in the category of schemes. And they give A1, actually. And this is the so-called J line. That's the J function that implements this. But this is not a good quotient. Not a good quotient. So one way of measuring that is that, for example, so on the moduli stack of elliptic curves, there's a natural line bundle that's denoted omega, which is kind of the dual of the one-dimensional vector space of tangent vectors at the origin. So it's the cotangent space of the, say, universal elliptic curve. Or in other words, you can write down a line bundle on this thing, which is actually equivariant for the group action, GM, or you can write down a line bundle on this variety, which is equivariant for this finite group acting, but it doesn't descend to the quotient. A1. So it's a bad quotient in the sense that you can have equivariant objects on the top, but they don't come from something on the bottom. And even more basic, the universal elliptic curve over the, so to speak, over this moduli space can't actually be defined over A1. There's no elliptic curve over A1, which is the universal elliptic curve. Okay. So what's the problem? Is that the action is not free. That's the basic problem. So there are some elliptic curves with extra automorphisms. Well, every elliptic curve has an extra automorphism, but okay, -1, yeah, but well, anyway. There are some elliptic curves with automorphisms. Because the action isn't free, the quotient is kind of collapsing too much. The naive quotient in schemes is collapsing too much. It's not remembering enough. And the solution is take the quotient in a more refined category. In fact, 2 category. So groupoids. So working in groupoids is, so this notion of groupoid quotient, it's a kind of a way of, so groupoid quotient. It's kind of a way of pretending that every action is free. So if you take a quotient in groupoids, if you have, say, a group acting on a set, and you take the quotient in groupoids, well, what that means is you're considering the groupoid whose objects are, say, elements of X and whose morphisms are elements of G, like mapping X to Y. So all of a sudden there can be lots of, if there's a fixed point, then you have many morphisms there. But there's always a map from X to X mod G, and the fibers are all isomorphic to G. Fibers in the sense of you take a pullback in groupoids like this. So the groupoid quotient always behaves like a free quotient. So it's always the X going to X mod G is always like the total space of a G bundle, so to speak. But the only trick is you have to interpret fiber in the sense of a fiber product in some 2 category. So an object here should be an object here and an object here with an isomorphism between them here. Or in other words, you have some fixed object here, and then you take an object here and make an isomorphism between its image and that one there, and then those are kind of by definition parameterized by G. So this is, yeah. So it's a way of taking a quotient such that you don't really care about the difference between a free action and a non-free action. And it's such that you formally have that line bundles on this quotient are the same as equivariant line bundles on X, and so on and so forth. But it does require passing to a 2 category. But okay, so this leads to notions such as Deligne-Mumford stack, or more generally, Artin stack. So these are all full subcategories of étale sheaves, say, on affine schemes. And so whereas in the discussion of schemes we had, well, Zariski sheaves, you could have also put étale there. It doesn't change anything in terms of the category of schemes. And you wanted them to be locally in the sense of open cover as represented by something here. Here you more or less require that you have a smooth cover by affine schemes. And really, there's maybe some technical things you want to put in there as well. So for the basic example, so it should look like you're taking an affine scheme, and maybe you're implicitly over some base, and then you have some smooth group scheme over that base, and then you pass to X mod G. So you have some G action on X, and then you pass to the quotient. In the stack theoretic sense, so in the groupoid theoretic sense. Okay. So these are more general geometric objects, and this is really good for moduli theory. And the theoretical justification for that is Artin's representability theorem, which kind of gives concrete criteria for when a functor is represented by an Artin stack. So CF Artin's representability. But it's still constrained by the need for a smooth cover. And in particular, this means finitely presented. So if you had some infinite group scheme acting on something, then some non-finite type group scheme acting on something, you wouldn't necessarily be able to take the quotient. Now you might say, why do you care? Well, just a second. So it turns out however, there are many objects, let's say X in, I don't know, étale, say, sheaves on affine schemes, which are geometrically relevant, but are not Artin stacks. Or not schemes, or not Artin stacks, or not whatever. So, so one example is formal schemes. So let's say you have a ring R, which is Noetherian, and then you have an ideal I in R, and you want to consider the formal spectrum. Well, there's different options as to how to encode this thing and what it should mean. One we've already discussed is kind of a Huber's theory, which includes formal schemes as an example, and is based on viewing this as a topological ring. Grothendieck's theory of formal schemes is also based on viewing this as a topological ring, but kind of on but localizing along a smaller subset than in Huber's theory. But another way of looking at it is it's just the collection of all it's just the union of all the nth order infinitesimal neighborhoods of R mod I and of spec R mod I in spec R. So you can, so kind of giving some data on a formal scheme, especially some sort of finite type data, I should say, should just be the same as giving compatible collections of data at all of these finite levels. So for example, vector bundles on Ri, so to give one of these, you should just give a compatible collection of vector bundles in the usual sense on, or finitely generated projective modules over these guys here. So that's a very different kind of gluing from what you think about with schemes, and even when you think about Artin stacks. I mean, there's no smooth covers in sight here. Instead, you're taking some union of infinitesimal thickenings, and you're getting a new object there. So there's other examples. So for some moduli problems, well, maybe I won't write this one, but for some moduli problems, you really are quotienting by an infinite dimensional group. So for example, the one that's dear to the hearts of homotopy theorists is the moduli of formal groups of dimension 1. I guess it's also dear to number theorists. Which is the Lubin-Tate space. And in this case, the group you have to mod out by is coordinate changes on kind of a one-dimensional formal scheme. And then there's infinitely many coefficients you have to specify. So it's like an infinite dimensional group you have to mod out by. And then it just doesn't fit into the framework of Artin stacks. So for example, maybe I'll write it, of formal groups. You have to quotient by an infinite dimensional group. So this suggests, for example, that you should use should go to a different topology, say FPQC instead of ATOL, if you want to accommodate some infinite type phenomena in your covers. But there's also, so in addition to these, there's also a kind of a very remarkable class of examples, which I'll put, so this started by Carlos Simpson, and the idea of this could be something like, so let's say every linear algebra category is quasi-coherent sheaves on some stack in a suitably generalized sense. And I'm sorry, I don't mean to say that Simpson exactly said this. This is kind of a, I mean, I don't, but his work was giving lots of examples of this kind of phenomenon where you have a natural linear algebra category, and then look, it turns out you can write down some stacks. That thing's quasi-coherent sheaves. This is my interpretation of, I mean, I'm stating something much too strong to be true, but it's just a heuristic to keep in mind. So, for example, and there are fun examples just in the world of Artin stacks. So, if G is an algebraic group, let's say over a field K, I don't know, then a special case of a non-free quotient is you take just a point with an action of G. So then the BG, which is the quotient of point by G in the groupoid sense. So a quasi-coherent sheaf on this should be a G equivariant quasi-coherent sheaf on the point. But then on a point, you're just getting a K vector space. And the G equivariance exactly means you have a representation of G. So G representation in K vector space. But also you can have things like, so if you look at A1 mod GM for the natural action by scalar multiplication, so this is a funny stack because there's an open locus in this stack which corresponds to a GM invariant open locus in A1, namely GM. So GM is an open subset here, closed under the GM action. And on that open locus, you're taking GM mod GM, which is a point. So this has a point as an open subset, so to speak. And then the closed complement is 0 mod GM. It's this previous thing. So it's a stack where you have an open subset, which is a point, and then a closed subset, which is BGM. OK? But so in this case, quasi-coherent sheaves, well, maybe I should say flat quasi-coherent sheaves if I'm sticking to the abelian context on A1 mod GM. This is the same thing as filtered K vector spaces. So Z-index filtration. So again, some fairly natural linear algebra category. It turns out to be quasi-coherent sheaves on a stack. But also, here's maybe the even cooler example. So so these are Artin stacks, so there's nothing exotic there. But then there's this interesting thing. So let's say K has characteristic 0, and then X over K is a smooth variety. Then you can form, and Simpson did, form what's called the de Rham stack of X. And what is it? Well, it's presented by, you take X, and then you're going to mod out not by a group action, but by just some equivalence relation. And the equivalence relation will be the equivalence relation which identifies 2 points if they're infinitesimally close to each other. So equivalence relations are supposed to live in the product. And what you do is you take this product and you formally complete along the diagonal. So and that will then present this thing here. And the formal completion should be taken in this sense here, of just the union of the specs of the different scheme structures that are available on the diagonal as a closed subset. Sorry? The definition makes sense in arbitrary characteristic, but some of the things I'm about to say will not be true. So what are quasi-coherent sheaves on this? Or let's say vector bundles. Vector bundles on X de Rham is the same thing as vector bundles on X equipped with some kind of descent datum, but that descent datum exactly amounts to a flat connection. That's kind of Grothendieck. Grothendieck's interpretation of what is a flat connection. It's kind of exactly giving descent, identifying infinitesimally close points. And then there's also cohomology, cohomology of the structure sheaf. This is de Rham cohomology. R gamma de Rham, X over K, which is the natural notion of cohomology, say in the world of vector bundles with flat connection. So this is it's not close to being an Artin stack either, and for different reasons from the moduli of formal groups, we're modding out by some formal scheme giving an equivalence relation, and it's just, yeah. Okay. Is there a question? Okay. So more recently, so Bott-Lurie, Drinfeld define stacks which capture coefficient systems, whose Q-co captures coefficient systems for various p-adic cohomology theories. In characteristic P or mixed characteristic or sort of in a limit over ZP. So, for example, for de Rham cohomology in characteristic P, there's also a stack. It's just not this one. You have to use the divided power or envelope of the diagonal instead of the formal neighborhood of the diagonal. And so there are stacks capturing prismatic cohomology, de Rham cohomology, crystalline cohomology, and also the comparison theorems in, say, prismatic cohomology. Between all of these various cohomology theories you have defined can be explained, so to speak, geometrically. It's arguable how geometric these kinds of stacks are, but geometrically in terms of the stacks. Maybe the better way to say it is that a priori these comparison theorems are about comparing linear algebra, like vector spaces or something. But it turns out there's a more fundamental explanation, which is that you just have an isomorphism of stacks. And then passing to quasi-coherent sheaves and looking at functoriality, you deduce comparisons of cohomology theories. So you promote a comparison of cohomology theories to an isomorphism of stacks. Okay. I want to give another example of this phenomenon, so this is de Rham cohomology in characteristic 0. I mentioned some p-adic cohomology theories as well, but what about Betti cohomology? So here's a fun example which actually has quite a bit of relevance for the course, so that's why I'm going to mention it, so Betti stacks. So I recall that Betti cohomology is the algebraic geometer's term for just like if you have a complex variety, then you take singular cohomology or sheaf cohomology with constant coefficients on the underlying topological space with the analytic topology. So for example, if you have S, say, a compact Hausdorff space, then I claim that you can make a stack. And how do you do it? You use the old familiar idea. You find a surjection from a profinite set. And then you have some fiber product, but that will be a closed subset of a product of two profinite sets, so it'll also be a profinite set. So then T0 and T1, that will also be a profinite set. So you have your compact Hausdorff space is a quotient of an equivalence relation in the category of profinite sets. And then you can map this over to the profinite set. You can associate spec of the ring of continuous z-valued functions, say, or k-valued functions if you're working over k, whatever you like. And then you get a groupoid in the category of schemes, category of affine schemes, in fact. And then you can define I don't know, Betti stack or something as the quotient of this equivalence relation now in the category of whatever sheaves for the FBQC topology on affine schemes. And what are quasi-coherent sheaves on S Betti? These are just usual sheaves of Z modules, abelian groups on this topological space. So that's a fun exercise. So coherent cohomology on this Betty stack is just usual topological cohomology of the topological space S. So, and more generally, you can kind of, more generally, you can kind of view a condensed set as some kind of stack. Just take the presentation you have in terms of profinite sets and then map it over to the world of stacks instead via this procedure. Okay.
The other question would set the meet read it.
Okay.
I guess here the Betty stack does not depend on the choice of T0.
That's correct.
That was a question.
That was the question? Yeah, okay. Yeah, I mean, yeah. You can show that what you have to check to see that is that, well, you have to check that if you have a surjective map of profinite sets, then it goes to a faithfully flat map on the level of continuous functions. That's not that hard to do. I mean, these things are just filtered colimits of continuous functions on finite sets, which are products of copies of Z as a ring. And so in fact, for any map of profinite sets, the map is flat. And then if it's a surjective map, you can see it's faithfully flat. And then you also need to see that fiber products in the category of profinite sets correspond to relative tensor products. And it follows again by the same kind of reduction to finite sets, using that this is just the filtered colimit of continuous functions on the finite quotients, which are kind of pure combinatorial objects. Yeah, so this thing is also kind of a T0 underline. It's just the inverse limit of the constant schemes on the finite sets. Okay. Right. Okay. So that was... Okay, so now we're faced with this somewhat baffling array of different stacks. Again, some of which don't resemble Artin stacks in the least. But we kind of want them because they're convenient ways of encoding different kind of linear algebraic phenomena, different kind of geometric phenomena. So then the question is, so the natural question, so how to define a reasonable full subcategory of, say, sheaves FPQC on affine schemes containing all these examples. Does anyone have any suggestions? I like your suggestion. Let's do it. So the answer, yeah, there is a reasonable full subcategory containing all of these examples, and it's this one. Well, modulus some set theory. So it's not, in other words, it's not clear that there's any. It's not clear that there's any other answer to this question than that one there.
What's the difference between there's question and answer?
Yeah. Well, in the question I ask for a full subcategory of this category, and in the answer I say, take the full subcategory, which is just the whole category. So there is content in the answer, but it didn't necessitate introducing anything that wasn't present in the question. What's that? What's that, Peter?
No, so it's a little bit of operating.
A little bit of what?
Use that.
I assume it's not important. I can't hear what you're saying, but yeah. Uh-oh. Oh, we've got some reverb. Does someone have their laptop open or something? Or? No. Ah. Okay. All right. So this is also the approach we will take in defining analytic stacks. So we will define a Grothendieck topology on affine analytic stacks, which is just the opposite category to analytic rings, and take sheaves with respect to it. Again, modulo set theory. Now, again, before getting into the details of exactly which Grothendieck topology and so on, I want to kind of continue this sort of discussion, but now talking about the kind of examples of analytic stacks that we want to be able to discuss. So, but maybe we'll take a 5-minute break first. Yeah, again, before getting into the details of what Grothendieck topology and maybe these set theoretic technicalities as well, I'd want to say what kind of phenomena are we trying to capture. So, what should examples be? So, well, in some sense, we've already seen some. So, we certainly want that any adic space, in the sense of Huber, should give rise to an analytic space. So we already explained how the basic ingredient in adic spaces, these Huber pairs, RR plus, give rise to analytic rings. And we explained something about how the formalism of analytic rings lets you glue, but we didn't quite, well, we saw that at least you can localize the category of quasi-coherent sheaves, or the category of modules over that analytic ring. You can localize it along Huber's spectrum. But we actually didn't quite discuss how you can use that to then glue these analytic rings together to get some kind of analytic space. But we certainly want that, the kind of gluing that shows up in Huber's theory, gluing along, say, rational open subsets in this topology defined by with a basis of rational opens. We want that kind of gluing to be allowed and to give you an analytic space. And we also want that, say, any complex analytic space should give you an analytic space. Say over this gaseous version of the complex numbers, or some p-liquid version of the complex numbers. So the kind of gluing allowed should also incorporate gluing along open subsets in complex analytic geometry. Well, another even more basic thing is we want the world of analytic geometry to be a generalization of the world of schemes. So we want, well, algebraic stacks. In some sense, maybe not precisely the sense that I was discussing with the FPQC topology and so on, a slight modification of that should give rise to, analytic space. I was going to use the word stack, I'm sorry. Analytic stacks. And this went over the sort of universal base Z. So this is with mod Z equals all of So kind of universally over any analytic ring, if you have some algebraic object, you can get an analytic object. Well, we would also like kind of, say, our Banach ring should definitely give rise to an analytic stack, which kind of matches, in some sense, Berkovich's theory. In the same way as these RR plus things we had, these affine analytic stacks match the Huber's picture. There's a small interesting tidbit here, which is that the stack that we'll assign to a general Banach ring will actually not be affinoid. It'll really be a stack. So if you take Z, the usual Archimedean norm, it will go to an actual stack that's not affinoid. So that's going to be, so it's kind of a stack which corresponds to the Berkovich spectrum of the integers in some sense. So that will be a fun little twist, which we'll discuss when we get there. What else? Well, we want various coefficients. So there should be analytic stacks capturing various, so whose Q co capture various coefficient systems. For cohomology. Maybe I should also mention we want to have the Tate curve. We want to be able to define the Tate curve plus its uniformization, over this this liquid base ring. Yes?
Gaseous.
What? Oh, thank you, gaseous. Thank you. Yes. Sorry, force of habit over this gaseous base ring. But we also want to know. To have machinery to prove it's algebraic. So we have this curve that we defined via uniformization. We take the analytic GM and we quotient by the multiplication by Q. And we get something which Peter argued was a smooth proper curve, and it has an identity section. So then if you have some Riemann-Roch theorem, then you can see that you have a projective embedding. And if you have some Gaga theorem, then you'll be able to see that it has to be algebraic. So we want Riemann-Roch, and we want Gaga. And on the theme of Gaga, we want that various linear algebraic comparison results should promote to isomorphisms of stacks. So Gaga is one such. Gaga is a general principle which applies in different contexts. But for example, in the world of complex analytic spaces, it says that if you have a proper algebraic variety over the complex numbers, so it has an analytification which is compact, and then it says that coherent sheaves and their cohomology in the algebraic and in the analytic sense agree. So that's a question about making a comparison between two linear algebraic categories. It's saying algebraic coherent sheaves are the same as analytic coherent sheaves. And one thing we would like our formalism to do is to promote that to an isomorphism of stacks. So And another example would be, say, again in the complex analytic context, would be the comparison between Betti cohomology and de Rham cohomology, another well-known comparison isomorphism. That should also promote to an isomorphism of stacks. So that's the kind of thing we want to discuss. And maybe I'll spend a little bit more time on this Gaga. So how could Gaga possibly be explained as an isomorphism of stacks? So so recall, so the adic geometry in the solid context really got started once we saw that there's a nice there's a nice subset of A1 over solid Z. Namely the closed unit disk, which we were thinking of as open, or you could think of it in terms of its complement, or the translation of that back to the origin. So in the end, this algebraically speaking, this came from an idempotent algebra. Which was actually just Z power series T in solid ZT Z, meaning just ZT modules in solid abelian groups, the thing which controls the affine line over Z solid. So once we had this idempotent algebra, then we could move it to infinity via the change of variables T goes to T inverse, and then that gave us the closed unit disk. And then that let us tie into the R plus theory, where we could ask that the elements in R plus actually land in the closed unit disk as opposed to just being maps to A1. So similarly, so if you're working over this this gaseous stack that Peter talked about last time, you can define a subset of A1. Sorry?
The word making clear that you invert Q.
Yes, thank you. Sorry. Yes. Thank you. Yeah. Can define a subset corresponding to an idempotent algebra. Well, morally speaking, it's functions which are convergent in some unspecified disk around the origin. So it's germs of functions defined at the origin, so to speak. So formally, it's going to be some filtered colimit. So some filtered colimit of this basic P guy, and then you can kind of do a multiplication by Q. And in contrast to the solid case, where this P guy actually was idempotent itself, and it turned into this guy, which exactly was idempotent. Here, this P will not be idempotent in ZT modules in this category. But when you take this colimit to shrink the something like the open unit disk down to the origin, then it does become idempotent. Um,
Yeah, sorry, we
Yes.
write sheaves, and what are they valued in 1-1 groupoids?
Yeah, so yeah, let's say groupoids. But of course, I mean, you might as well, yeah. I mean, I don't, but all the examples are just groupoids. And in fact, many of the examples, even though they're called stacks, are actually just sheaves of sets. So like Simpson's de Rham stack, for example, it's just a sheaf of sets. It's a de Rham space somehow. But anyway, somehow they call these things stacks anyway. But yeah. So it's going to be similar to the situation with analytic rings, and where we had sometimes theoretically we had derived things that were animated or whatever and so on. Theoretically we had them, but in practical examples they didn't really show up. And similarly here, theoretically we're going to allow sheaves with values in anima, but in practical cases they'll be at most groupoids. I mean, that's, yeah. Okay, right, so, and this lets us, again, import, and it satisfies, this idempotent algebra satisfies many of the same properties as that one there. And it lets us import, again, Huber's theory of pairs to this context. So what you do is you take this thing, so idempotent algebra functions germs at the origin in the affine line. You move it to infinity and you get germs at infinity. And then for a given algebra over just the usual underlying ring of this gaseous base ring, you could ask that you could take the analytic ring structure, which is just R modules in the gaseous category, but then you could require, in the sense of analytic stacks, that all those, for every element in your ring, all the maps to A1 that you have, the map you get to A1 given by that element actually lands in this subset, which is away from infinity, so to speak. So that was a mouthful. So e.g., so if R is, say, finite type over the usual underlying ring of this thing, for example, then you can, then for any f in R, you get a map, so to speak, from spec R. Then, first of all, you get an analytic ring structure on R, where you have R and then just R modules in this this gaseous space. Then you get a map from spec of this thing to A1 given by F, and then you can pass to the subset, or the subspace of this spec R, where all such land in the locus away from infinity, in the sense that you're killing that algebra, the idempotent algebra object you get by moving your functions germs in 0 to germs at infinity. And this, in examples, gives you a new analytic space, the analytification. The analytification. So, for example, the analytification of GM, so if we take R to be, whatever, the base change of Z, t plus or minus 1, new variable t, this is exactly the object in Peter's talk. that you use that you quotient by in order to get the Tate curve.
Shows a specific function, yeah, right? I mean, here you set up a definition that depends on f. No?
Ah.
There.
Oh.
Take f to be 0.
That's true. Yeah. That's true. So, yeah, you're absolutely right. But it turns out, again, it's part of the general formalism that if you just require it for t and t inverse, then you automatically get it for all elements in this ring. So,
take the 0. If you take 0 in R, and you do this construction, then what happens?
0?
Yeah.
Well, then you're definitely away from infinity. So the condition is automatic.
That's okay, sorry.
Yeah. No, it's okay. Yeah. Okay. So, right. So, okay. So that. So then it
Not quite right, Dustin.
What?
At this point, yeah, it's not quite right. Scarcity space ring, we can go basically to Archimedean infinity, and in Archimedean infinity, the function 2 is unbounded. The number 2 is a function. It's unbounded near the Archimedean infinity. So technically speaking, the way you set it up, you're ignoring this very Archimedean point there. It's fine, but since the statement you wrote on the board is not technically correct.
You're saying it's not correct that if I have two functions that are that land away from infinity. What?
The sum of two bounded functions is not bounded.
The sum of two bounded functions is not bounded. Ah.
Who is that?
Yeah. I did mess this up. Thanks to both of you.
Now I realize here you have 0 and there you have infinity, and that confuses me.
Oh yes, but that's because, right, so I was building what in this analogy is analogous to the closed unit disk. So now I'm actually a little bit confused about what's going on here.
I mean, it's only the simulation happening against this Archimedean infinity point, which is a bit unusual.
Oh, I see what you're saying. Yeah, it's because the Archimedean branch is going all the way out. Yeah.
It's all the way, there's even close points and all.
Ah, okay. Okay. So what I was saying is actually not correct. So my apologies and thanks to the commenters. So it does not fit all of the, so if you...
I think you can make it as you did, but then you just automatically localize away from this point.
Yeah, right. Right. Okay, so yeah, so probably what we should do is we should only work over, we should probably add an extra axiom to our, well, we can shrink the spec of this ring as well. We should add the axiom that all the integers are bounded, say. So will this fix the problem, Peter?
It should fix the problem.
Yeah, so, and then the claim should work that all the Huber's theory of pairs transports to this context. And we won't lose, for example, the Archimedean theory over the real numbers or the complex numbers by this procedure, since there the integers are bounded. So I apologize for the mistake, but thanks again to the people for correcting me. So this won't be exactly the object in Peter's talk. This will be the object in Peter's talk when you base change to a ring where Z is bounded. So in the same sense of, yeah, where all the elements in the integers are bounded.
Just 2 is bounded enough, right?
2 is bounded is enough, okay. Yeah. Okay. So, okay, right. So now, so there are these two different contexts in which you can import sort of Huber's theories of pairs into the world of analytic spaces, and it turns out that they can be glued together. So the solid and gaseous theories can be glued. Whoops. And the idempotent algebras as well. So if you look just over, so the gaseous theory makes sense over ZQ, in fact. So all we had to do to define the gaseous theory was we had to write down this endomorphism of P, this 1 minus Q times T, and then ask that it become an isomorphism in our theory. And to do that, you didn't need to require Q to be topologically nilpotent. Yeah, so this gives ZQ gas. And so what happens if you set Q equal to 0, you get the uncompleted Z theory. If you set Q equals 1, you get the solid theory. And if you require Q to be topologically nilpotent and a unit, you get the gaseous theory. But in fact, so this is, but if you work away from this locus, so if you away from the locus of topological nilpotence, then you are working over a theory where you've forced both Q and Q inverse to be gaseous. And that implies that 1 is gaseous, which means you're in the solid theory. So you actually just get ZQ plus or minus 1 solid. So the solid theory for this here. So then then we can define a certain quotient of ZQ plus or minus 1 gaseous, meaning make Q gaseous, of spec of this, rather, which more or less parametrizes choices of a notion of analytification. So notion of analytification. So anytime you have this variable Q, which you've declared to be gaseous, you can form this colimit, and you'll get an idempotent algebra at 0, and you can move it to infinity, and then you get a notion of analytification as discussed. Maybe I should add this axiom here. But different choices of Q can give rise to the same thing. So if they differ by a bounded unit, if the two choices of Q differ by a bounded unit, so something in GM analytic, then you'll get the same algebra. So basically, the quotient you want to describe is given by taking this ring and modding out by multiplication by bounded units, multiplication on Q. So now we have, this is a different roll of stacks. In the theory. So here we have a stack. It's a quotient of an analytic ring by an equivalence relation, or spec of an analytic ring by an equivalence relation. And it is a stack which is in some sense parameterizing choices of analytic geometry over a given base ring. And then for any analytic ring R plus a map spec R to this stack, so to speak, mod GM analytic. So that could be called a gaseous structure on spec R. And let's say such that 2 in Z is bounded. We get a theory of analytification. So we get a functor. Well, we really get 2 functors from R schemes, say, to analytic stacks over R, plus a natural transformation. So namely, you get so x to x. Well, let's say x is spec A. So A is an R algebra or R underline algebra. I mean, so R star. So from usual algebraic geometry, on the one hand, you can take A, which is a scheme, but you can base change it to the uncompleted. I mean, you can view it as an analytic stack over the uncompleted Z, and then you can base change that to R. But then you also have this subset, it's analytification over R, given by requiring that all the functions land in the part of A1 that's away from infinity. And then there's a general theorem. So the general result on Gaga is that if x to spec R is proper, and maybe I should add finitely presented, then this map is an isomorphism.
Why did you put the final presentation?
Because I thought back to the last time I tried thinking about this, and I used that hypothesis. But yeah, so proper in general only means finite type, right? It was because of the fact that...
It's always something proper finitely presented.
What's that?
That's always close to something proper finitely presented.
Yes, but the problem I ran into when I was thinking about this was that, yeah, so for example, in the solid theory, to understand the solid like R mod I theory in terms of the solid R theory, if I is an ideal in R, we kind of, to do the calculations, we kind of needed to resolve, we needed to know that R was Noetherian to make the resolution. I mean, to know that the compact projective generators were products of copies of R mod I, when you just take the relative solid theory of R mod I in R. So that was a technical point that I wasn't quite sure how to address in setting up the formalism with lower stars and so on. But I agree, but maybe that's not actually relevant for the Gaga statement. But I think it's going to be relevant for something. If it's not relevant for this, it's probably relevant for proper push forwards, like lower star equals lower shriek or something like that. But let me just keep it in there to be safe. Okay. So then remark, taking, so this implies completely formally that some version of derived category on the analytification is the same as derived category on the algebraic guy, which is some version of Gaga, and then implies non-formally. And maybe need more conditions on R, technical conditions on R, that, for example, vector bundles. I mean, technical conditions, but quite general. So, and so on, the classical Gaga.
By XR, you mean base change of X to R?
Yeah, exactly. Okay. Yeah. So you take your algebraic. So that's one of the things that maybe I should have been emphasizing before launching into this whole discussion, is that over the uncompleted Z theory, you basically can do algebraic geometry, and then that means you can do algebraic geometry over any analytic ring just by base change. So that's kind of like considering the affine line, like I was considering the affine line, for example, over an arbitrary base ring. It's not analytified yet, but when you have extra structure on your analytic ring, then that picks out a choice of what it means to analytify also an algebraic variety. And so,
And what's the compensates? X is affine, or?
When I was describing kind of explicitly what it is, I was looking at the case where X is affine, but in general, both things glue. And so then you can define, you can, it doesn't need to be affine, no. Yeah. So all classical Gaga theorems are special cases. So there's, so for example, Grothendieck's formal Gaga, well, the complex analytic Gaga. So Serre's original Gaga, you take, for example, C gaseous or P liquid or whatever you like. There's also formal Gaga, which is, if you have again, complete Noetherian ring, and then you have a proper scheme over it, then coherent sheaves on that is the same thing as coherent sheaves on the formal scheme you get by formally completing, or in other words, compatible collections of coherent sheaves on all the various nilpotent thickenings there. Then you would take spliff, well, maybe I should say SPA. So in terms of Huber pairs, you would work over this, which lives over a solid Z. And therefore inherits the notion of analytification from solid Z based on the closed unit disk. It also includes like non-Archimedean Gaga, say over over QP or any complete non-Archimedean field. So there you would take your analytic ring, you would take to be a spec of, say, QP solid. But you wouldn't put the gaseous structure on it, which factors through the map to spec Z. Rather, you'd put the gaseous structure on it, which corresponds to mapping to spec of Z Q hat plus or minus 1 Q gaseous, where Q goes to P, say. So say standard choice of topologically nilpotent unit. That's the one that picks out the notion of analytification that corresponds to usual analytification of algebraic varieties over your non-Archimedean field. You could have also chosen the other gaseous structure on this guy where you factor through spec Z solid. And And that would give you a different statement of Gaga, in fact, a different theorem. So yeah, so remark N3 could also choose the solid Z gaseous structure on solid QP. That gives an a priori different Gaga theorem.
Wait, what's the implication of A1 on this?
Oh, the analytification of A1 will then just be the open unit, the closed unit disk. So, yeah, let me illustrate.
That cannot be. The analytic QP is not very bright, it's QP crosses automorphisms.
It has what? Sorry?
The analytification, the algebraic variety A1 of a QP.
Yeah?
You can rescale the QP crosses automorphisms. So they must also act as automorphisms of the analytification of A1. So I think the analytification of A1 in that context is.
Oh, wait. Ah, you're right, I'm sorry. Yeah, that open unit disk is when you just force T to be analytic, but there's no reason why that should also force something like T over P to be analytic. Yeah, no, it's the same Gaga. Thank you. Yeah, I miss, I was.
Not the same Gaga, it's just some.
No, it is the same, isn't it? Because you would make.
Again, comes the FMI becomes empty. Like a point, like you should always assume that your whole base consists of.
Ah. You're right, I forgot that axiom. Shoot. Yeah, so I'm sorry, you need, oh boy, thanks again. So you need to assume that every element in here is bounded. Yeah. So I was kind of making the same mistake again over and over. Yeah, I'm sorry. So you don't get a Gaga statement at all in this context because 1 over P is never going to be, if you try to make 1 over P bounded in that sense, then you're just going to kill everything. So in the solid QP setting. But nonetheless, there's a point I wanted to make, which is that there is still a different gaseous structure on solid QP obtained by taking obtained by factoring it through solid ZP. And in a sense, the difference between this gaseous ring structure and this gaseous ring structure is sort of the difference between usual rigid geometry and some kind of over-convergent version of rigid geometry. Yeah. Okay. So.
Is there something weaker than N?
Something weaker than N? Could you explain the question?
Is there a result that would identify XR with some less regular?
Could you explain?
Okay, maybe.
Okay, yeah.
This assumption that this F is bounded.
Yeah, yeah.
So, what is the issue if you don't assume that? It's empty, like the.
If you don't assume that everything in here is bounded, then when you try to do the analytification in the sense that I described, then in particular you're always forcing all of the scalars, i.e. elements of here, you're forcing them to become bounded anyway. So if you don't have this assumption, then your analytification will be actually changing your base. So a special case is when you take x equals spec r and you try to analytify that. What this assumption is saying is basically that then it doesn't change it. That like spec r is its own analytification. If it weren't, you would just work over you just work over some analytic ring where this thing has been forced to be bounded. But in the case of solid QP, if you try to force, with that gaseous structure factoring through solid Z, if you try to force all of the scalars to be bounded, you're just going to get the 0 ring. Because, yeah. Yeah. Right. Yeah. So that was the, x equals spec r was giving a problem there. My apologies. Okay. Right. So that was kind of explaining one example of where a linear algebraic comparison result can be promoted to an isomorphism of stacks. More generally, we want relations. So relations between the various kinds of stacks, various examples. So already in Peter's talk, he had this map from the Tate curve with parameter q to the topological circle. So, and we want this to make sense as a map of analytic stacks. So where I already explained how such a thing is an algebraic stack, and algebraic stacks will embed into analytic stacks even over the initial analytic ring. And then we have the Tate curve, and so this kind of analytic space should map to that kind of analytic space. But also if X is a complex analytic space, then you want X to map to its underlying topological space, X of C. And if, say, R is a Banach ring, then you want its, well, sort of its liquid spec to map to the Berkovich spectrum. So there's all these, we're going to have all these various different classes of analytic spaces, and we want the category to be such that we can make maps between them when we expect comparisons. So for example, it's well known that the coherent cohomology of a complex analytic space localizes on the underlying topological space. That's kind of more or less by definition in a lot of ways. And that kind of linear algebraic relation is supposed to be explained by the existence of such a map in this large category of analytic spaces. All right. I think maybe I'll say one word about the set theoretic technicalities just to get it out of the way. So addressing well, let's go back to our algebraic analog. So this was the opposite category of commutative rings. So we have FPQC sheaves on there, but again, this is not a legitimate definition because this is not a small category. And this, by definition, is a full subcategory of functors from commutative rings to, say, sets or groupoids or whatever you like. And there's well-known problems with such things that the morphisms in this functor category involve some more than a set's worth of data. So you have morphisms that aren't sets but are some sort of bigger entity. So that's a real pain. So what is the fix? Consider, so instead of presheaves on AF, consider what are called accessible presheaves. Which are the same thing as accessible functors from commutative rings to sets. And what are accessible functors? If and only if there exists a cardinal kappa, regular cardinal, such that functor f, such that f commutes with kappa filtered colimits. So what does this mean? The first choice of kappa is L of naught. And in general, when you think of a regular cardinal, you shouldn't try to think about what it is as a set. What you should really think of is the collection of sets that are of smaller cardinality. That's what kappa is really indexing. Don't think of it as the cardinality of some set. Think of it as indexing the, so this corresponds to finite sets. Those are the sets of cardinality smaller than kappa. And then the notion of kappa filtered colimit in that case is just the usual notion of filtered colimit. So if your functor commutes with filtered colimits, you're OK. But if kappa gets bigger, you have fewer kappa filtered colimits. So so for example, if you take kappa equals L of 1, then you're indexing the countable sets. And you're only then a kappa filtered colimit would be one where every countable set has a cone, as opposed to just every finite set. So there are fewer kappa filtered colimits. That means there's more examples of functors which commute with kappa filtered colimits. Kappa. So the nice thing is that for every x in AF, the Yoneda its image under the Yoneda embedding is always accessible. And in fact, accessible is equivalent to being a small colimit of representable functors, HXs. So if we think of these affine schemes as the basic building blocks and colimits as our gluing procedure, then we're saying kind of an obvious thing. We're only allowed to glue a set's many worth of things together at a time. And that's exactly what's captured by this notion of accessible functor. And moreover, FPQC sheafification preserves accessible sheaves, or presheaves, sorry. That was actually a theorem of Waterhouse. So that you can, so that you can also impose the sheaf condition at will without running into set theoretic technicalities.
But this accessible precious is not presentable, right? Category.
It's not a presentable category.
Nevertheless, there is a left-hand simplification.
Yes.
Okay.
Yeah.
We have to prove it, or
Yeah. It has to be proved. So what makes this work? So these are not kind of, in some sense, non-trivial claims, the claims made here. So what makes this work? So the first thing is that this category that we're working with is presentable. In fact, compactly generated. That's what makes the theory of accessible presheaves work. So it makes that the condition there commuting with kappa filtered colimits is the same as being a small colimit of representables. And then there's something about the Grothendieck topology, which is that every FPQC cover in AF is a filtered, there exists a kappa such that, and in this case it's LF1, is a kappa filtered limit of kappa compact FPQC covers. So every flat cover of a ring is a LF1 filtered colimit of countably presented flat covers of that ring. And this kind of condition, having some a priori bound on the basic FPQC covers, a priori cardinality bound, is what you can use to check this kind of FPQC sheavification result. And so maybe I'll say then, well, at least, we haven't explained what our Grothendieck topology is, but we've at least explained what the category of analytic rings is. So there's a theorem. So analytic rings is presentable. In fact, it's kappa compactly generated for kappa 2 to the aleph naught plus. So that kappa small means cardinality less than continuum. So that's what lets you kind of formally avoid all of these set theoretic difficulties involved with taking presheaves and sheaves on a big category. And maybe maybe I'll add well, no, I won't add anything. That's fine. Okay, thank you for your attention.
this category of analytic rings is naturally enriched over condensed animal, right? I mean, mapping space is a condensed animal.
Yes.
So we could also consider enriched sieves instead of usual sieves. It seems also natural to me, but it is take non-enriched things.
We take non-enriched, yeah. And it's confusing. It's confusing. What can I say?
So in particular, this analytic, the category of analytic stacks is not enriched over condensed sets?
No, it's not. That's right. Yeah.
It is, right? In a different way. Because light condensers are also meant to.
Okay, but how do you use that to get an enrichment?
Enrichment.
I mean, yeah, well, maybe there's some adjoint functor. I mean, you're saying, I mean, okay, yeah, it's not even clear it's enriched over itself, right? Well, I mean, I don't know, yeah. But no, I guess you're right. You're saying you just take your profinite set or whatever, and then you cross it with X and map it to Y. Yeah, no, yeah, that's right. Yeah, so there is sorry, thanks, yeah. So you could take, so in analytic stacks is enriched over light condensed sets because you can define an S-valued point to be just a map like this. But it's different from the enrichment. There's essentially no relation with the enrichment you had on analytic rings because we imported these things via kind of very trivial analytic rings, just continuous functions in it. Yeah, it's all in all, it's a little bit confusing. And yeah, so for example, I think in some recent works with p-adic coefficient systems, and like Visha Nijol was telling me that she wants to work with like sheaves of solid abelian groups on the proatoll site, and then you know on the proatoll site you already have profinite sets there, so you're somehow you're doing condensed in two orthogonal directions at the same time. But apparently that's the correct thing for her, and it's just it's all a little bit confusing, but yeah. Yeah.
I want to explain how this Berkovich space can be seen as an analytic space.
Well, by this I just meant the topological space, and maybe I make some assumptions to make sure it's compactly generated. Otherwise, I mean, sorry, metrizable. Otherwise, I have to modify a little bit what I mean, maybe. But yeah, just so the same way that, that this thing was a topological space and therefore an analytic stack. So, but this you could think of as providing an analytic stack structure on this, a non-trivial analytic stack structure on this topological space here. Yeah.
What do you mean by 2 is bounded?
What do I mean by what?
Like 2 is bounded. 2 is bounded.
2 is bounded. Yeah, so what I meant was that so we have some spec R, and I was looking at the affine line, and then, so 2 is a function on this. Well, if you have any element in the ground ring, it gives you a section of the projection, and you can ask that that section be away from the local ring at infinity. So we had this ring of ring living at the origin, this filtered colimit of P along scaling the coordinate by Q. And then we can put it at infinity, and we can ask that this F not meet that locus at infinity in the sense that, well, in the sense that if you take some relative tensor product like R mod F and then that ring that lives there, then you get 0. Right, and if that happens, we say that F is bounded, or that F is kind of analytic. So it doesn't get too close to infinity. So you have to ask that condition for the scalar 2 in order for some of the claims I made to hold. Yeah, and for the Gaga, you have to ask that condition for all elements in the base ring. Yeah, I feel particularly silly about forgetting that because, I mean, basically, we already basically wrote up the argument in the previous lectures on complex analytic spaces, and that axiom was explicitly included there, so I just kind of forgot about it. Okay. Other questions?
Maybe at some point you said, so you wrote, what was the gaseous structure on spec R?
On spec R?
Yeah. You said that this amounted to a map to spec R Q plus minus 1 gaseous divided by GM.
Did I say spec R Q plus minus 1? I meant spec Z Q plus minus 1.
Okay, I mean, okay.
Ah, okay.
You wrote spec R Q, I guess. But
Oh, I'm sorry. I'm sorry.
with spec Z.
I meant Z. I'm sorry.
But is it possible to elaborate it? Or maybe in some other time. But
Well, I mean, the point is that if you have a map to that stack, then you get to define such a ring, the ring of germs at 0, which lets you run this machine of building analytification. So
yeah, but so why do you divide by GM? And it's because you don't really want to specify.
exactly, you don't want to specify Q. So for example, you know, if you have like a Tate ring or whatever, an Tate-Huber ring or whatever, then there exists a topologically nilpotent unit, but you know, it doesn't play any role. I mean, or at least up to some bounded difference, it doesn't play any role. So that's exactly what this quotient is doing. It's saying you have some, say, topologically nilpotent unit, but it should only matter up to some bounded difference. And so you define this GM analytic, and then you say that if you have Q and you multiply it by something bounded both away from 0 and away from infinity, then that should play the same role. In particular, it should give rise to the same idempotent algebras and the same theory of analytification, and so on.
By the way, I don't think you multiply Q by bounded, something bounded. I mean, it's rather that, but you can either multiply by something of norm 1, or you raise it to some power. Right.
But it's
I think it gets confused. So the thing you multiply is not really an analytic GM at all.
It is.
I mean, you can have something that's like Q that's not bounded norm itself, but if you multiply by something bounded that's too large, then you would actually not have something proposing nilpotent anymore. Right?
Yeah, but that's true. That's true. Wait.
There is some quotient, but it's not really.
I thought I wrote the thing down.
But maybe we can just sort this out with some challenge.
I thought I wrote this thing down. Just a second. Ah, okay. Sorry. Yeah, maybe it's not the GM. Maybe it's the. So you can also define the locus where the coordinate is bigger than or equal to 1, or sorry, in some overconvergent sense, and the locus for t is less than or equal to 0. Maybe it's the thing that's that lies in between there.
That's all.
That's not a. Yeah, that's a group. Yeah.
No. We will discuss later in the course.
Yeah. But now I'm concerned. Okay, anyway. Okay, we'll discuss it later in the course. Thanks, everyone.